Okay, so we are going to continue our discussion on the characteristics of rolling and slipping. This is going to be the third video in this sub-series, and if you recall, the type of problems that we are addressing in this sub-series is basic rolling and slipping motion of disks or spheres, and the idea is to understand the different the interplay between the friction forces and the resulting dynamics under different slipping conditions. So we started off by making the basic observations that if there is a disk that is rolling and slipping, then the condition for rolling without slipping is that the point P, which is the point of contact with the ground, is instantaneously at rest, and that basically implies that the velocity, the linear velocity with which the disk is moving, is equal to the angular velocity times r. And of course the direction of the linear velocity and the angular velocity must be such that they represent a consistent rolling without slipping. So that's the condition for rolling without slipping. Then what we said was that there are two different conditions, two different scenarios, therefore when this rolling without slipping is going to be violated. Since the equality is the condition for rolling without slipping, the two conditions by which this equality can be violated is if the initial velocity is greater than the initial angular velocity times r, or if the initial velocity is less than the initial angular velocity times r. And keep in mind that the situation that we are trying to analyze is that we are giving different types of initial conditions, and we are trying to see how the motion is going to evolve. So in the first two videos on this sub-series, we considered the scenario where the initial linear velocity is greater than the initial angular velocity times r. So as a result of that, what we have noticed is that the point of contact with the ground would have a net forward going velocity v naught minus omega naught r, and that would cause the friction force to be in the backward direction. And then based on that, we derived the equations of motion. We were able to solve the equations of motion, and what we noticed was something very interesting. We noticed that the friction force is such that when v naught is greater than omega naught r, the friction force tries to reduce v naught and increase omega naught, so that eventually the velocity and becomes equal to the angular velocity times the radius. And when that happens, the disk has reached the condition for pure rolling, and at that instant, from that instant onwards, pure rolling resumes. And this is considering ideal rolling situation, where in pure rolling there is no energy loss. So it is almost like the friction is manifesting itself in such a way that it's trying to make the velocity to become equal to the angular velocity times r. So it reduces the linear velocity and increases the angular velocity times r, and then causes them to be eventually equal to each other. So that was the first scenario, and we did this derivation. We derived all the conditions. We derived the velocity of pure rolling, angular velocity of pure rolling. We also showed that the indeed during the slipping part, where the linear velocity decreases and the angular velocity times r increases, the net kinetic energy actually decreases because of friction. And it then when the disk reaches the configuration of pure rolling, it then maintains that energy level as the pure rolling occurs. So in this video, what we are going to do is we are going to take the second scenario, where the initial linear velocity is less than the initial angular velocity times r. So let's look into that scenario, and we'll contrast it with this first scenario that we have considered. So now we are going to consider scenario 2, and here V0 is less than omega naught R, right? So let's sketch the free body diagram as usually the case. So the angular velocity initial is omega naught, like this. The linear velocity is V0, so this is the initial condition, and here is the contact point with the ground, and of course the radius of this disk is R. Now if we consider the velocities, now to remember that to determine the direction of friction, what we need to do is find out what is the relative velocity between the ground and the point of contact of the disk with the ground. Okay, and remember that friction tries to oppose that relative velocity. So friction tries to make that relative velocity go away. It tries to make that relative velocity go to zero. So to be more specific, when we try to find out the direction of friction when two bodies in contact are slipping, we need to look at the relative velocity at the point of contact, and keep in mind that the friction will try to reduce the relative velocity. So at this point P, if the disk was just translating without rotation, then the velocity of the point P would have been V0. So this would have been the velocity if so V0 would be the velocity if this disk was not spinning. On the other hand, if the disk was only spinning but not translating, then the point P here would have had the velocity omega naught times R. Now we have assumed that omega naught times R is greater than V0. So that's why I have drawn this arrow or this vector to be larger than this vector. So as a result, as you can see here, the velocity at the point P, the velocity of the point P is then equal to omega naught R minus V0, and it is in the negative. So if I consider this to be the x direction, then it is in the negative x direction, so negative I, right? So the friction force, so that's the velocity of the point P at this instant. So therefore the friction force at this point on the point P on the disk is going to be in this direction. So here you see, although the disk is moving forward with a velocity V0, okay, sometimes intuitively, if we don't understand this detail, we may just put the friction force to be backwards, but that's not the case here. Here the friction force is actually acting in the forward direction, in the direction of the velocity, and is because of the fact that although the disk has a forward velocity, it has got a very high spin, and because of that the contact point with the ground, which is the point P, has a relative velocity with respect to the ground in the backwards direction, which is omega naught R minus V0. So the friction, what it tries to do is it tries to oppose that relative velocity and provides a force in the forward direction. Now the force is of course mu times the normal reaction, and that we have shown by N, and there is a gravitational force mg here. So this is very interesting. I would like to now contrast this. First I need to show the gravitational acceleration here. Let's contrast this with this earlier free body diagram. So you see here in this earlier free body diagram, the friction force was backwards. Now the friction force is forwards. The friction force was backwards initially because V0 was greater than omega naught R, which means that the point of contact with the ground was having a relative velocity forward. So the friction was trying to oppose that relative velocity by giving a force in the opposite direction. Here the case is just the reverse. Okay, so then let us then write our equations of motion. This is the angle of direction of positive theta. So we'll say that let me just make sure that my conventions are all the same. Mx double dot, IC theta double dot, omega is what we are using, normal reaction. Okay, mu is the coefficient of friction, and so yeah, so essentially we have mx double dot is equal to so this is of mass m and x is the forward direction, so that is equal to the friction force, and that is going to be mu times n, and that is going to be mu times mg, right? If I express this in terms of velocity, then m vx dot is equal to mu mg. Okay, so that's going to be my first equation. And the rotational equation, if this point is the center is C, then the rotational equation is going to be IC theta double dot is equal to the summation of moments. Now the force F is producing a counterclockwise moment, and theta is defined to be clockwise, positive clockwise. So then the moment produced by this force is a negative moment. So we have minus Fr, so minus mu nr, so it is equal to minus mu mgr. Okay, and if I express theta double dot as omega dot, then I have IC omega dot is equal to negative mu mgr. So that is equation 2. Right, so therefore from 1 we have the following. We have Vx dot is equal to mu g, which means that Vx is equal to V0 plus mu gt. So immediately what we can see is that here the dynamics is playing out in a way that the velocity is increasing because of the friction, and that is clear because the force is in the direction of the positive x direction. So the force is actually an accelerating force. So clearly, in terms of the translation, the force is going to cause the velocity to increase. On the other hand, you can see that the torque that this force is providing is a negative torque. And so from 2 we have IC omega dot is equal to negative mu mgr, implying omega minus omega naught is equal to minus mu mgr divided by IC t, or in other words, omega is equal to omega naught minus mu mgr over IC times t. And since we have been comparing not the angular velocity with v, but rather angular velocity times r, so it's probably appropriate to right away express the variable omega times r. So omega times r is equal to omega naught times r minus mu mg r squared over IC times t, right? And for a disk, IC is so IC is equal to half mr squared. So IC is half mr squared for a disk. So if we substitute that here, we are going to get omega r equals omega naught r minus I'm going to substitute half mr squared, so it is going to become minus 2 mu gt. Okay, so that is going to be my equation 4. So again, we can see here that the angular velocity times r is going to reduce and the linear velocity is going to increase, right? And so in this case, what friction will do is it will keep increasing the linear velocity and decreasing the angular velocity, and it will keep doing so until the angular velocity times r becomes equal to the linear velocity, at which point pure rolling is going to take place. So remember, in the first scenario, we had a case where the velocity decreased from v naught and omega r increased from omega naught r, and there was a point where they would become the same and pure rolling would ensue at that point. In this case, we are going to have the situation where the following is going to take place. So we have omega naught r, and let's say v naught is here. Keep in mind that we have considered the scenario where omega naught r is greater than v naught, so I have shown both of them to be positive but omega r to be a greater positive number. So you can see that omega naught r is going to reduce with a certain slope, and v is going to increase with half the slope. So you can see the slope of this is negative 2 mu g, so whereas the slope of this is mu g. So this slope is mu g and this slope is negative 2 mu g, and this is of course with time. And there is going to be a point where, let's call that t star, where the velocity will become equal to the angular velocity times r, and at that point we are going to have pure rolling. So essentially we will have pure rolling beyond this t star, and here before t star we are going to have slipping. Right, so this is the scenario, and similar to the last time, we can actually find out at what time, or how much time will it take for this slipping to end, and at what time, that is it going to transition to pure rolling. So transition, and that can be found out quite easily, to pure rolling occurs when v is equal to omega r. So we can find that condition out by imposing v naught plus mu gt, and let's call that instant t star, that is the velocity at the time t star, is going to become equal to omega naught r minus 2 mu g t star. Okay, so this condition is imposing the condition that v becomes equal to omega r, and we can solve for t star from here, because we see 3 mu g t star is equal to omega naught r minus v naught. So therefore t star is equal to omega naught r minus v naught minus 3 mu g. So it is at this instant. So t star is equal to omega naught r minus v naught divided by 3 mu g. So it is this instant that the slipping is going to stop and the disk is going to transition to pure rolling, and from this point on pure rolling will ensue. So this is we'll stop with this brief presentation. As you see, this was scenario 2. Here we showed how the direction of friction changed, but in both cases, scenario 1 and scenario 2, you saw that friction was instrumental in making sure that the slipping ultimately transitions to pure rolling. And so this is a very important feature of friction that we see from studying these two scenarios. In the following video, we will, just like for scenario 1, we will show what is the drop in the kinetic energy, and also what are the actual velocities and angular velocities when the rolling happens, when the pure rolling happens. That can be figured out quite easily from the equations that we have derived so far. So that is it for this video. Thank you so much.